Welcome to the first episode of our new series, To the Stars and Beyond. In this series, we'll dive deep into the wonders of the universe, from the stars that illuminate our lives to the farthest mysteries of the cosmos. And where better to begin this journey than with the Sun, the central star of our solar system and the origin of nearly all life on Earth. In today's episode, we focus on the Sun. We'll explore why it plays such a pivotal role in sustaining life, its influence on humanity throughout history, and why it has been a symbol of energy, light, and inspiration for millennia. Let's take a closer look at the science, history, and profound significance of our nearest star. The Sun is far more than just an astronomical body. It is the engine of life on Earth. Without its light and warmth, there would be no photosynthesis to provide oxygen and food, no water cycle to sustain ecosystems, and no climate systems to shape our planet. The Sun's influence goes beyond biology. It drives the physical and chemical processes that define our planet's systems. It regulates the seasons, governs weather patterns, and provides the energy that makes Earth a vibrant and dynamic world. Without the Sun, Earth would be a cold, barren rock. But with it, our planet flourishes as a beacon of life in the vast expanse of space. The Sun has not only ensured humanity's survival, but has also profoundly shaped our cultural and spiritual development. Throughout history, the Sun has been a symbol of power, eternity, and divine presence. Its cycles, sunrise and sunset, solstices and equinoxes, have always been central to timekeeping and the creation of calendars. Take Stonehenge in England, for example. This ancient stone circle is precisely aligned to mark the solstices, demonstrating how deeply early humans connected their lives to the Sun's movements. For them, the Sun was not just a source of warmth, but also a cosmic guide and a spiritual beacon. In ancient Egypt, the Sun was worshipped as the god Ra, the creator of life. The pyramids, aligned to the rising sun, symbolized a bridge between the earthly and the divine. Similarly, the Inca in South America revered the sun as a deity. Their sun temple, Coricancha, in Cusco, was an architectural marvel covered in gold, which they poetically called the sweat of the sun. Even in today's world, the Sun's influence persists. Our calendars remain tied to the solar year, and solar energy stands at the forefront of sustainable technology. The Sun continues to illuminate not only our physical world, but also our aspirations for a better, brighter future. It all began in a massive molecular cloud, a collection of gas and dust that stretched across light years. This cloud was composed primarily of hydrogen and helium, the most abundant elements in the universe. However, it also contained heavier elements like carbon, oxygen, and iron, remnants of earlier generations of stars that had exploded as supernovae. Normally, a molecular cloud is stable, but external forces, such as the shock wave from a nearby supernova or the collision with another cloud, can trigger its collapse. Gravity took hold, pulling parts of the cloud together and increasing its density. This marked the beginning of our story, the formation of a protostar. As gravity drew more and more material inward, the cloud began to spin, much like an ice skater pulling their arms in to spin faster. This rotation caused the cloud to flatten into a rotating disk. At the center of this disk, the densest and hottest region, most of the mass accumulated, and pressure and temperature increased steadily. After millions of years, the temperature at the core grew high enough to ignite nuclear fusion. A star was born, our Sun. The ignition of fusion marked the transition from a protostar to a main sequence star. At this stage, the Sun began producing energy by fusing hydrogen into helium. a process that continues to power its brilliance today. While the Sun was forming at the center, the surrounding disk underwent its own fascinating transformation. Tiny dust grains began to stick together, initially through electrostatic forces and later through gravity. These clumps of dust grew larger and larger, eventually forming planetesimals, objects that could span several kilometers in size. In the hotter inner regions of the disk, rocky and metallic materials dominated, leading to the formation of the terrestrial planets: Mercury, Venus, Earth, and Mars. In the cooler outer regions, gases like hydrogen and helium gathered around larger icy and rocky cores, forming the gas giants Jupiter and Saturn, as well as the ice giants Uranus and Neptune. At this stage, the young solar system was still a chaotic place. Planetesimals collided frequently, and many smaller objects were flung out of the disk by the gravitational influence of larger planets. Simultaneously, the Sun's solar wind, a stream of charged particles, swept away the remaining gas in the disk. After about 100 million years, the solar system settled into the more stable arrangement we see today. The Sun has started its fusion processes. But what does that mean? What can we imagine about this? To do this, we have to descend into the interior of the Sun. At the heart of the Sun, something incredible happens. Hydrogen nuclei, protons, fuse to form helium. This process occurs in several steps. First, two protons collide. One proton transforms into a neutron, forming a deuterium nucleus, or heavy hydrogen. Along the way, a positron, the antimatter counterpart of the electron, and a neutrino are released. This is the first step of the proton-proton chain. In the second step, another proton collides with the deuterium nucleus, creating helium-3, a light helium isotope, while releasing gamma radiation in the form of a photon. Finally, two helium-3 nuclei fuse to form helium-4. In the process, two protons are released back into the cycle. The result is helium, energy, and a neutrino. This energy is what makes the Sun shine so brightly and sustain life on Earth. But why can protons fuse in the first place? Normally, they repel each other because they are both positively charged. This is called the Coulomb barrier. It's like trying to push two magnets with the same pole together. In the Sun's core, however, three key factors come into play. First, the temperature in the core reaches an incredible 15 million Kelvin, making the protons move fast enough to approach each other. Second, the pressure is immense, squeezing the protons closer together. And third, quantum mechanics allows protons to overcome the Coulomb barrier through a phenomenon called quantum tunneling, even if they don't have enough energy. Without this effect, fusion in the Sun would be impossible. Fusion produces two key types of particles: neutrinos and photons. Neutrinos are tiny and almost massless. They interact very weakly with matter, meaning they can leave the Sun's core almost unhindered. A neutrino takes only a few seconds to escape and travel to Earth. Photons, on the other hand, have a very different journey. In the Sun's dense core, photons constantly collide with electrons and atomic nuclei. Each collision changes their direction or absorbs and re-emits them. This process, known as radiative transfer, significantly slows their progress. The Sun, our central star, might appear as a simple, glowing sphere at first glance. However, it is actually made up of several distinct layers, each with unique physical properties and functions. To understand the processes that make life on Earth possible, we'll take a detailed look today at the layered structure of the Sun and the remarkable characteristics of each of its zones. The Sun consists of 6 main layers, ranging from the innermost core to the outer corona. These are the core, the radiative zone, the convective zone, the photosphere, the chromosphere, and the corona. Each layer plays a specific role in generating and distributing energy. Let's start with the core, the powerhouse of the sun, and work our way outward to the corona, where sunlight and solar winds transition into interstellar space. The core, the powerhouse of the sun. At the very center of the sun lies the core, the region where all of its energy is produced. The core extends across about 25% of the sun's radius and is an extremely dense and hot area with temperatures reaching up to 15 million Kelvin. Here, the process of nuclear fusion takes place, specifically the proton-proton chain, where hydrogen nuclei are fused into helium. The conditions in the core are extreme. The density is about 150 times that of water, and the pressure reaches an incredible 200 billion atmospheres. These conditions allow protons to overcome their natural electrostatic repulsion, the Coulomb barrier, through quantum tunneling, enabling the fusion reactions that power the sun. The radiative zone, the slow journey of energy. Surrounding the core is the radiative zone, which extends out to about 70% of the sun's radius. This is where energy produced in the core is transported outward primarily through radiation. Photons, or particles of light, are repeatedly absorbed and re-emitted by surrounding particles, a process known as radiative transfer. The journey of a photon through the radiative zone is incredibly slow and chaotic. A single photon can take anywhere from 100,000 to 1 million years to traverse this region due to constant scattering. The temperature gradually decreases in the radiative zone, from around 7 million Kelvin at its inner boundary to about 2 million Kelvin near the outer edge. The convective zone, the bubbling outer layer. Above the radiative zone lies the convective zone, which stretches from about 70% of the sun's radius to its surface. Temperatures here range from 2 million Kelvin near the bottom to roughly 5,500 Kelvin at the top. In this zone, energy is no longer transported by radiation, but by convection, the physical movement of hot plasma. Hot plasma rises toward the surface, releases heat, and then sinks back down as it cools. This movement creates convection currents that resemble the bubbling motion of boiling water. The convective zone is also responsible for surface phenomena, such as sunspots and granulation patterns, which are visible evidence of this turbulent layer. The photosphere, the sun's visible surface. The photosphere is the thin outermost layer of the sun that we perceive as its surface. It is about 400 kilometers thick and has a temperature of approximately 5,500 Kelvin. This is the region where light escapes into space, making it visible to us on Earth. However, the photosphere is not uniform. It features structures like granules, caused by convection currents, and sunspots, which are cooler, darker areas formed by intense magnetic activity. Despite appearing solid, the photosphere is a gaseous layer with low density. The chromosphere, the sun's colorful halo. Above the photosphere lies the chromosphere, a thin layer about 2,000 kilometers thick. The temperature in this layer increases dramatically, from roughly 4,500 Kelvin at its base to around 20,000 Kelvin at its top. During a solar eclipse, the chromosphere appears as a reddish ring around the sun, a hue produced by the emission of hydrogen atoms. This layer plays a key role in solar activity, including flares and prominences, which are driven by the sun's magnetic field. The corona, the mysterious outer atmosphere. The outermost layer of the sun is the corona, an expansive and highly dynamic region extending millions of kilometers into space. Surprisingly, The corona is much hotter than the layers below it, with temperatures soaring to several million Kelvin, a phenomenon that remains one of the great unsolved mysteries of solar physics. The corona is the source of the solar wind, a stream of charged particles that influences the entire solar system. It can be seen during a total solar eclipse as a glowing white halo. Events such as coronal mass ejections, CMEs, originate in this layer, releasing massive amounts of energy and particles into space that can impact planets, including Earth. Currently, the Sun is in the main sequence phase of its life, burning hydrogen in its core through nuclear fusion. This is the most stable and longest phase of a star's life, and for the Sun, this phase will last around 10 billion years in total. With about 4.6 billion years already gone, the Sun is roughly halfway through its main sequence journey. During this phase, the Sun's core maintains equilibrium between gravity pulling inward and the pressure from fusion-generated energy pushing outward. However, this balance won't last forever. In approximately 5 billion years, the hydrogen fuel in the Sun's core will become depleted. Fusion will slow, and the balance between gravity and radiation pressure will begin to shift. Gravity will cause the core to contract, increasing its temperature. This contraction will trigger the fusion of hydrogen in a shell surrounding the core, while the outer layers of the Sun will expand. This marks the beginning of the Sun's transformation into a subgiant. As the Sun evolves further, it will enter the red giant phase. This stage is characterized by a dramatic expansion of the Sun's outer layers, which will swell to engulf the orbits of Mercury, Venus, and possibly even Earth. The Sun's radius will increase by hundreds of times, and its surface temperature will decrease, giving it a reddish hue. While the Sun's outer layers cool, the core will continue to contract and heat up. Eventually, the core will reach the temperatures needed to ignite helium fusion, a process called the triple alpha reaction, where 3 helium nuclei combine to form carbon. This phase will last for about 1 billion years, during which the Sun will lose a significant amount of its mass through powerful solar winds. These winds will scatter material into space, contributing to the cosmic cycle of star formation. When the helium in the core is depleted, the Sun will no longer have the necessary energy to sustain its outer layers. These layers will be ejected into space, creating a stunning planetary nebula, a glowing shell of gas and dust surrounding the remaining core. Planetary nebulae are not only breathtaking to observe, but also crucial for enriching the interstellar medium with heavier elements like carbon and oxygen, which are essential for the formation of new stars, planets, and even life. What remains after the planetary nebula fades is the Sun's core, now a white dwarf, a dense Earth-sized remnant composed mostly of carbon and oxygen. No longer producing energy, the white dwarf will gradually cool and dim over billions of years. White dwarfs are incredibly dense. A sugar cube-sized portion of one would weigh tons. Although they no longer support fusion, white dwarfs can emit residual heat and light for trillions of years before becoming black dwarfs. Hypothetical objects that have cooled completely and no longer emit any energy. Eventually, after an incomprehensible span of time, the Sun will cool to the point where it becomes a black dwarf. By then, the universe itself may have changed dramatically, with stars having burned out and galaxies drifting apart. It's important to note that no black dwarfs currently exist because the universe is not old enough for white dwarfs to have fully cooled. This makes the Sun's ultimate fate a concept rooted in theoretical physics and far beyond our own temporal experience. As we've seen, the Sun is not just the heart of our solar system, but also its timekeeper, with a life cycle spanning billions of years. Its story reminds us of the interconnectedness of all things in the cosmos, from the hydrogen in its core to the planets that orbit it, to the life that thrives on Earth. But our journey doesn't end here. To truly understand the solar system, we need to explore its components one by one, starting with the planet closest to the Sun, Mercury. A scorched world of extremes, Mercury bears the brunt of the Sun's power. It's a planet of blazing heat during the day and freezing cold at night, with a mysterious history etched in its cratered surface. Thank you for joining us on this cosmic journey. Until next time, keep looking up. The universe is waiting.